In the second part of the discussion on step potentials, let us consider the case that total energy of the incident particles is less than the height of the potential value. Okay, so we have two regions, x less than 0 and x greater than u. Okay, this is the plot of the potential energy. Okay, so this is region 1 and this is region 2. Okay, in region 1, if we write the Schrodinger equation, so this is region 1. It is d square time independent Schrodinger equation, right? D square by dx square phi 1 plus okay, so it is 2m by h cross square e minus v, but v is 0 here, so 2m by h cross square e. Okay, phi 2 equal to 0. This is same as the previous case also. Okay, so let us put k1 square, or let's I'll simply use k square. Okay, k square equals 2m by h cross square into e. So we have d square by dx square. This is phi 1, right? So d square by dx square phi 1 plus k square phi 1 equal to 0. Again, this is simple harmonic motion equation as in the previous case of E greater than U. Let us write the solution in terms of complex exponentials. So we have a e raised to I kx plus b e raised to minus I kx. It's the same as in the previous case. Only difference is that instead of k1 I have used only k. So we know that when you add the time dependent part, this represents the incident wave traveling in the plus x direction in region 1, okay, and this represents the reflected wave traveling in the minus x direction in region 1. Okay, so let us, that's about region 1. Then now region 2. In region 2, in this region, if we write the Schrodinger equation, it is d square by dx square phi 2 plus 2m by h cross square e minus v, but v is equal to u in region 2, so e minus u phi 2 equal to 0. But here, since energy is less than u, this entire term is negative. Okay, so in order to introduce a positive constant, what we have to do is let us take this one negative side outside from this. So we have d square by dx square phi 2 minus 2m by h cross square u minus e phi 2 equal to 0. Now let us put alpha square as 2m by h cross square into u minus e. E is less than u, so u minus e is positive. Okay, so alpha square is positive. So I am introducing another constant. So the reason I am not using k2 square maybe, or this is k1 square and this is k2 square, is even though alpha has the dimension of 1 by length, okay, you can check that. That is, its dimension is same as that of a wave number, but this cannot be, alpha cannot be interpreted as a wave number. We will see the reason shortly. Okay, so if I use this, we get d square by dx square phi 2 minus alpha square phi 2 equal to 0. Now, what is the solution of this equation? This equation is called a diffusion equation, right? Or the differential equation for the process of diffusion is this type of an equation. Now, you can check that the solution of this equation phi 2 can be, it will not be a complex exponential like this. That means it will not be sine function or cos function or a combination of both. Okay, this, when you introduce complex exponentials, it means the solution is a simple harmonic function. So this solution is not such a harmonic function. Its solution is either e raised to alpha x or e raised to minus alpha x or a combination of both. So in general, I can write phi 2 is equal to c e raised to alpha x plus d e raised to minus alpha x. So you can check that e raised to alpha x is a solution of this, e raised to minus alpha x is also a solution of this. So since it's a linear homogeneous differential equation, a linear combination is also a solution. So mathematically this is the general solution of this one. But there is a problem here. Even though mathematically e raised to alpha x and e raised to minus alpha x are okay, are solutions of this, physically there is a problem with this part. The problem with this part is that as x tends to infinity, because in this region for x greater than or equal to 0 our potential energy is u. So this region goes up to infinity. So the limit of this region is plus infinity. So as x tends to plus infinity, this e raised to alpha x tends to infinity. Okay. But one of our admissibility conditions is that for the wave function to be square integrable, as x tends to plus or minus infinity, the wave function should go to 0. So if we retain this part, this wave function will not be normalizable or integrable, square integrable. Okay, it's not a normalizable wave function. So this part has to be discarded because of the quantum mechanical admissibility conditions. So my point is that even though this part is a perfectly acceptable solution of this equation, from a mathematical point of view, this is not a physically acceptable wave function for a matter wave, because it doesn't satisfy our this boundary condition that it should be a normalizable wave function. So we have to discard this. Then what is the expression for phi 2? Phi 2 we can write as d e raised to minus alpha x. Okay, so this is phi 1, let me call it equation 1, this is equation 2. So phi 1 is essentially an oscillatory solution. Okay, it's a sinusoidal or simple harmonic type solution. That means we have a wave here, a traveling particle here. A harmonic wave represents a traveling particle. So this is the incident wave, this is the reflected wave, that's fine. But phi 2 doesn't represent a traveling wave. It is simply an exponentially decreasing wave function. So this shows that the wave function will exponentially decrease in region 2. There is no oscillating part, there is no oscillating wave functions. That means there is no traveling wave in region 2. Okay, but there is some wave function in region 2. So the point is that even though total energy is less than the height of the potential barrier, something like consider a beam of particles, a beam of electrons coming to a grid, where the kinetic energy of the beam of particles is 10 electron volt, the grid potential is minus 20 volt. So the kinetic energy is less than the height of the potential barrier, which is 20 electron volt. Okay, but still the wave function in region 2 is non-zero. There is some wave function, even though it is exponentially decreasing, there is some wave function in region 2. So when you go to a large distance in region 2, the wave function will go to 0 because it's exponentially decreasing. Okay, so as x increases, this will decrease fast. But still there is some wave function here. That means the square of the wave function gives you probability density of finding the particle. So there is some probability of finding the particle in region 2. Okay, so even though the energy of the incident particle is less than the height of the potential barrier, there is a non-zero probability of finding the particle in beyond the potential barrier. Okay, this phenomenon is called quantum tunneling. Okay. Before we go to boundary conditions, let us try to plot the wave functions in region 1 and region 2. So as before, let us try to plot the wave function superimpose the wave function in the plot of the potential energy function. Okay, this is the potential energy, its height is u. Total energy is less than potential energy, so let us say this is the total energy of the particle. So in region 1, the particle is oscillatory. There is a traveling particle. But when you come to region 2, its wave function exponentially decreases. So this is the plot. Okay, in region 2, the wave function exponentially decreases. So there is some probability of finding the particle in region 2 up to some distance. Okay, we can call it some penetration depth. The particle penetrates to region 2 up to some distance, but we cannot call it as a traveling particle. If we measure, there is some probability we may find the particle here, but that doesn't mean that it's a traveling particle. It is, in the strict sense, we cannot say that the particle is traveling in region 2 because the wave function is in region 2 is not a oscillatory wave function. Now let us try to apply the boundary conditions as in the previous case, and I am going to calculate the reflection probability as before. So these are the wave functions. Let us define reflection probability. Reflection probability is the fraction of the reflected particles, right? So what is the reflected wave? This is the reflected wave. So let's call this as phi1 plus, this as phi1 minus. Okay, so reflection probability is mod phi1 square. We can say mod phi1 minus square v1 divided by this intensity of the reflected wave, okay, or proportional to the intensity of the reflected wave, and intensity of the incident wave is phi1 plus square v1. Since both are in region 1, incident wave and reflected wave, velocity will be the same. Okay, so this is equal to mod b square by mod a square. Okay, phi1 minus is this part, so its square is mod b square, v1 will cancel, and phi1 plus square is mod a square. We will come back to the question of transmission probability a little later. First let us calculate reflection probability. So we need the relationship between b and a. Okay, for that let us apply the boundary condition. So as before, at x equal to 0, the condition is that phi1 should be equal to phi2. Okay, that is wave function in region 1 should be equal to wave function in region 2. That is the continuity of the wave function. So what is phi1 at x equal to 0? A plus b. And what is phi2 at x equal to 0? D. A plus b equal to d. And similarly at x equal to 0, the second boundary condition is that the derivative of phi1 should be equal to derivative of phi2, space derivative. Okay, so what is the derivative of phi1 here? I k a. X equal to 0, we get exponential, exponential part will be 1, and then next is minus I k b is equal to, derivative here is minus alpha d. Okay. Okay, so we can simplify this equation. We can write a minus b is equal to, I can take ik outside from these two, so ik times a minus b equal to minus alpha d. Ik we can bring to the right side. 1 by I is minus I, so we get I alpha by k times d. Okay, so by adding these two terms, we get, as before, let us call this as small a, this as small b. So we get a plus b gives, adding these two, b will cancel, we get 2a is equal to 1 plus I alpha by k times d. So a is equal to 1 by 2, 1 plus I alpha by k times d. A minus b. When you subtract, we get 2b. 2b is 1 minus I alpha by k into d. So b is equal to 1 by 2, 1 minus I alpha by k times d. Therefore, what is the reflection probability? Reflection probability is b square mod b square by mod a square, which means b star by a star. Now we can see that a and b are complex terms, complex coefficients. So what is b star? B star is okay. So we have b into b star. Then we have 1 by 4 into, okay, 1 by 2 into 1 by 2, and this into its complex conjugates, 1 minus I alpha by k into 1 plus I alpha by k. So we get 1 plus alpha square by k square times mod d square. This is mod d square divided by, what is mod a square? 1 by 2 into 1 by 2 we get 1 by 4. 1 plus I alpha by k into its complex conjugate. 1 minus I alpha by k. So we get 1 plus alpha square by k square times mod d square. Numerator and denominator are the same. So we get the result that reflection probability is 1. Okay, so when E is less than U, okay, when the energy is less than the height of the barrier, reflection probability is 1. That means if 100 particles per second are incident on the potential step, all the particles will be reflected back. Okay, that is the meaning of this one. Reflection probability is 1. So if reflection probability is 1, what is the transmission probability? 0. That means in here we cannot say that the particles are transmitted to region 2, because in region 2 we don't have a traveling particle. The only point is that we have some probability of finding the particle there, but it cannot be treated as a traveling particle. So the idea is most of the incident, maybe 100 particles per second are incident here. Then almost 95 particles, let us say 95 particles are reflected at x equal to 0. Some of the particles will move to region 2 up to some penetration depth, and then they will also be reflected back. So ultimately all the 100 particles per second are reflected back. That's why reflection probability is 1. Maybe a large number of particles are reflected at x equal to 0. A small particles will travel to some distance inside region 2. Okay, that is called some distance delta x, some penetration depth delta x, and then they will be reflected back. So there will be some quantum tunneling, but ultimately all the particles are reflected back. That's why reflection probability is 1. So if reflection probability is 1, we cannot talk about a transmission probability. Transmission probability is 0 in the strict sense. Okay, this type of penetration we cannot call it as a transmission of particles. Okay. Another reason we cannot talk about a transmission probability is, how do you define transmission probability? Something like we have to define transmission probability as phi 2 square v2 divided by phi 1 plus square v1, right? But the problem is, the idea is that the question is, can we define something like this? Okay, so we know that phi 2 square is the probability density in region 2, right? Probability per unit length, and v2 is velocity, distance by time. So we get this is number of particles per unit. Okay, phi 2 square is proportional to number density. So the idea is that this must be proportional to number of particles per unit time. The problem with this definition is that this velocity v2 is negative in this. Velocity is imaginary in this region, because kinetic energy is negative in this region. Okay, why? Because in this region, total energy is less than potential energy, right? If total energy is less than potential energy, kinetic energy must be negative, right? So kinetic energy negative means kinetic energy is half mv square. If kinetic energy is negative, velocity will be imaginary. So we cannot define a velocity in region 2. So in that sense, we cannot say that the numerator is number density. So we cannot talk about in number density of particles in region. No, we cannot talk about number of particles per unit time or intensity of particles in region 2. So if we cannot define intensity of particles in region 2, we cannot define transmission probability. So this definition is not valid. This is not possible. So in that sense also we cannot define a transmission probability. So we can only say that there is some probability for the particles to penetrate to region 2, but ultimately all the particles will be reflected back. So that's the meaning of reflection coefficient equal to 1. Now let us try to plot how the reflection and transmission probabilities vary with energy. From the situation that total energy greater than potential energy step, we have this following information. When energy is very much greater than potential energy, then we have seen that reflection probability tends to 0 and transmission probability tends to 1. Okay, all the particles are transmitted. And when energy is exactly equal to u, we have seen that reflection probability is 1 and transmission probability is 0. Always r plus t is 1. And we have also seen that when energy is equal to 1.03 times u, very close to u, slightly greater, then reflection probability and transmission probability are equal, and each of them is equal to 0.5. From E less than U case, when total energy of the incident particles is less than the height of the potential step, there is only one situation, that is okay, in this case we can say reflection probability is 1 and transmission probability is 0. Okay, even though some of the particles are reach the other region on the other side of the potential step through quantum tunneling, we cannot say that that is transmission. There is no traveling particles on the other side. Okay, so reflection probability is 1. So with this idea, if we plot reflection and transmission probability together the same using the same coordinates, okay. Let us take energy along the x-axis. Suppose this position stands for E by, I'm plotting E by U along the x-axis. Suppose E by U is equal to 1 here, 2 here and 0 here. Okay, so E by U equal to 1 means E is equal to U. Okay, and the maximum value, we know that this is maximum. Let's call it, this is 1, and somewhere here is 0.5. Okay, so what is the nature of reflection coefficient? For E by U less than 1, that is for E less than U, reflection coefficient is 1. For E equal to U also, reflection coefficient or reflection probability is 1. Then for E greater than U, it rapidly decreases. So it's like this. Okay, the graph is like this. And what about, so this is the graph of reflection probability. What is transmission probability? For E less than U or E by U less than 1, transmission probability is 0. And then for E greater than U, transmission probability starts increasing. For E very much greater than U, transmission probability becomes 1. Okay, so it goes like this. It's almost equal to 1. So this position, or where R is equal, this is the graph of transmission probability. When R is equal to 2, R is equal to T, the value of energy is, or E by U is equal to 1.03. Okay, at this position, transmission probability and reflection probability are equal, which is 0.5. Okay. So this is the plot of combined plot of reflection probability and transmission probability for step potentials. So even though we have seen that even though transmission probability is 0 in this situation, there is some probability of finding the particle in region 2. For example, probability density is non-zero. We can perfectly talk about probability density, which is proportional to number density of particles. So which means that there is some probability density, there is some number density of particles in region 2. But we cannot say that they are traveling particles. Okay, ultimately all the particles are reflected back. So what is the penetration depth of the particles in region 2? Since the wave function is exponentially decreasing like this, e raised to minus alpha x, we can say that the penetration depth delta x is of the order of 1 by alpha. Okay, delta x is of the order of 1 by alpha. It is exponentially, for example, if delta x is of the order of alpha, we can say that the wave function will be exponentially e raised to minus 1. Its value will be decreasing. So if x is delta x is twice alpha, 1 by 2 alpha, okay, then it will be e raised to minus half, something like that. It goes decreasing. Or if we talk in terms of probability density is proportional to e raised to minus 2 alpha x. So if delta x is of the order of 2 alpha, we can say probability density is exponentially go to e raised to minus 1. Okay, so in general we can say delta x, the penetration depth is of the order of 1 by alpha. Okay, from here also, incidentally from here you can see that alpha has a dimension of 1 by length, just like k. But we cannot call alpha as a wave number because the wave function in region 2 is not an oscillatory wave function. So in that sense it's not a traveling wave. So alpha cannot be, even though its dimension is 1 by x, 1 by length, it cannot be interpreted as a wave number. That's why we have not used k here. Okay. Now what we are going to do is, so from Schrodinger equation we have got this result. We have seen that reflection coefficient, reflection probability is 1 here. All the particles are reflected. We have a incident wave and reflected wave in region 1, but in region 2 the wave is exponentially decreasing, and we can talk about a penetration depth of the order of 1 by alpha. This much result we have obtained from Schrodinger equation. Now what we are going to do is, let us try to analyze this from the point of view of uncertainty relationship between energy and time, and let us try to arrive at an expression, an independent expression for penetration depth. Okay, so here we ask the question, we conclude from Schrodinger equation that the wave function in region 2 is non-zero. Particles indeed are reaching region 2, they are getting penetrated to region 2 up to some length, even though they are reflected back. So, but in region 2, the strange situation is that it's a classically forbidden region. Why? Because here the energy of the particle, see, this is the energy of the particle which is less than the potential energy. So, in region 1, this total energy is same as kinetic energy, but in region 2, this is the potential energy, okay, whereas this is the total energy. So, if you look at this difference is U minus E, which is negative of kinetic energy. Kinetic energy is E minus U, total energy minus potential energy. So kinetic energy in region 2 is negative. Negative kinetic energy is not allowed, so it's a classically forbidden region. So then we can ask the question, then how do we think about this particle reaching region 2? In order to reach region 2, particles need some energy. It has to overcome this potential height, potential step, and reach region 2. Okay, how much, if it gains some energy to reach region 2, suddenly when it reaches this potential step, it gets, some of these particles gets enough energy to region 2, cross this potential barrier. How can it be possible? How do they suddenly gain this energy? Is it in a violation of, is it not a violation of conservation of energy? Then what we can see is that there is this time energy uncertainty relationship, that delta E into tau is of the order of h cross. Where tau is the, if a particle can exist in an energy store, or it can undergo a process. Suppose the energy, the error in energy involved in that state or a process is delta E, then and the time interval of that process or the energy state is tau, then there is a relationship like this. Okay, so this relationship says that there is one possibility of this relationship is that there can be small the violations of conservation of energy, okay, involving an amount delta E, provided this process takes place within a time interval tau, which is of the order of h cross by delta E. Okay, so if the some energy conservation in error in violation of conservation of energy happens by an amount delta E, if that process takes place within this time, if that process happens or that reaction takes place within this time, then we will not detect it. That's the idea. Okay, if this much error will always be there in a process taking place within a time tau. So if our violation conservation of energy is within the error which we cannot detect, then we will not be able to see this violation conservation of energy. So within the energy error obtained by this uncertainty relationship between energy and time, within that error where we cannot observe the violation, there can be violation in conservation of energy. Such a possibility is there. So let us consider that here also this penetration happens by some violation of conservation of energy, but that violation will not be detected if it happens within this time. Let us start with this idea. First of all, ask the question, what should be the extra energy required for the particles to reach region 2? Okay, so when these particles reach the boundary, what is the difference in between its energy and the height of the potential barrier? This much, right? U minus E. Okay, its energy is only E, but the height of the potential barrier is U, so they need this much energy to overcome the potential barrier. In addition, if their energy is simply U minus E, they will not cross over to the boundary, cross over to region 2, because they are able to overcome, but there is not much energy to travel, to move to region move further or penetrate further. So we can say that the energy that the particle required is one U minus E type, some this much energy is required to overcome the potential barrier. In addition, there should be some kinetic energy to move to a penetration depth delta x. Okay, so this much is the energy, U minus is the energy required for crossing the potential height and the potential step, and in addition, if some energy is there, some kinetic energy is there, it can reach there. So if this is delta E, see, it's like particle is suddenly gaining this much, some particles are suddenly gaining this much energy. So it's a violation of conservation of energy, but this is allowed if this much energy is obtained within the time interval tau, which is h cross by U minus E plus k. If this energy is higher, then tau will be much lower. Okay, as particle requires more energy, the time interval will be much smaller. Okay, this is the idea. So let's assume that some of the particles are obtaining this much energy spontaneously. Okay, within this time interval. Okay, so with this time interval, this particle must be moving to some distance delta x in region 2, and they must be coming back. So when they come back, their energy is lost. So suddenly the particle are getting some energy, they get penetrate through some distance and they come back. See, this is only a way of looking at it. Actually, this is not happening. We cannot say that the particle is traveling, moving forward and backward always. We cannot say like that. This is only a in order to get some mental picture, we are thinking like that. Okay, we have to keep in mind that. So within this delta, this time tau, the particle should cross over to delta x and then come back. Okay, so we can say that this delta, so 2 delta x, or the particle travels a distance 2 delta x is of the order of, okay, v times tau. Suppose the velocity of the particle in region 2 is v, okay, then what the time interval it takes to move to some delta x and come back is tau, then the distance traveled is 2 delta x, twice the penetration depth, that's equal to velocity into tau. Okay, so then let us try to get an expression for delta x. Delta x is half v into tau. Let us substitute. What is v? The kinetic energy of the particle is k, so we can say that kinetic energy is equal to half mv square, so velocity is equal to 2k by m. Okay, so instead of v I can substitute square root of 2k by m. Instead of tau I can substitute h cross by u minus e plus k. Remember that we are arriving at this expression by using uncertainty relationship, so we get only an order of magnitude, not an exact value. Okay. So this is an approximate expression, or order of magnitude of delta x, penetration depth. Now we can see that, let us consider two limiting cases. Suppose k tends to 0. Okay, if k tends to 0, then it means that if k tends to 0, velocity of the particle in region 2 is very small, tends to 0. If v tends to 0, then this penetration depth delta x tends to 0. From here also, if k tends to 0, this term will go to 0. This is nothing but velocity. So delta x goes to 0. On the other hand, if k is very large, suppose k tends to infinity, suppose the particle has very high kinetic energy. If k is very large, then the time within which this process has to happen becomes very, very small. Tau tends to 0. Okay, tau tends to 0 and delta x tends to 0. See, one more point regarding this k tends to infinity case is, you have k here in the numerator, you have k here in the denominator. But in the numerator it is root k, in the denominator it is k. So we can say that overall this delta x is proportional to 1 by root k. This root k is here, this k is here. So it is overall it is proportional to, we can say this root k and k cancels. Then overall behavior is proportional to 1 by root k. So if it is proportional to 1 by root k, then as k tends to infinity, this term increases, this term also increases, but overall effect is more for this term. Okay, so delta x goes to 0 in that case. Okay. On the other hand, when k tends to 0, this term clearly goes to 0. In the numerator also it goes to 0. In that case also delta x goes to 0. Okay, so in the two extremes, delta x goes to 0. So we want to find out what is the intermediate value of k. By varying k, let us try to find out what is the intermediate value of k for which delta x is maximum. So I am going to differentiate this expression with respect to k, putting it is equal to 0, and then see what is the maximum value of penetration depth. I have rewritten the expression of delta x in this way so that the k terms will come together. So let us differentiate delta x by or dx by dk. Okay, so dx by dk is this is a constant, and here we have the quotient rule. So we have u minus e plus k, derivative of the numerator 1 by 2 root k minus root k times derivative of the denominator, which is 1, divided by u minus e plus k whole square. Okay. So let us take this 1 by 2 root k outside. So we have h cross by root 2m, 1 by 2 root k. In the brackets we have u minus e plus k minus 2 times root k into root k is k, divided by u minus e plus k whole square. Now when you put this dx by dk equal to 0, when delta x or dx is maximum, its derivative should go to 0. So I have to put d by dk of delta x, right? D by dk of delta x. Okay. So d by dk of delta x goes to 0. Then what you get? This is these terms. Numerator goes to 0. This is a constant. So what you have is u minus e plus k minus 2k is equal to 0. So what you have is k is equal to u minus e. So for this value of k, delta x will be maximum. So let us find the maximum value of delta x. Therefore delta x maximum is of the order of, again, x cross by square root of 2m. Instead of k, I am substituting this. So we have here square root of u minus e divided by u minus e plus and this value of k is u minus e again. So we have 2 times u minus e here. So then one u minus e will cancel. So we have h cross divided by 2m into u minus e, square root of 2m into u minus e. Okay. And this value is the same as alpha, 1 by alpha, sorry. So of the order of 1 by alpha. H cross by 2m into u minus c. Remember the expression for alpha, square root of 2m by h cross square into u minus c. If you take that h cross to the numerator, we get this. Okay. So there is a 2 also here, right? U minus c plus u minus c will be 2 times u minus c, and one root will cancel. So there is a 2 also here, extra 2 here, 1 by 2. So we get 1 by 2 alpha. Okay, so maximum value of delta x is of the order of 1 by 2 alpha. This 1 by 2 we can neglect, so we can simply say that maximum value of delta x is of the order of alpha, because from uncertainty relationship we get only the order of magnitude. Okay, so even this 1 by 2 we can neglect. So the point is that from the purely the consideration of uncertainty relationship between energy and time, we have anticipated that this penetration happens because of a small violation, an apparent violation in conservation of energy. So this violation can happen within a small time interval of the order of h cross by that delta E. Then with that consideration we have arrived at this relationship, delta x maximum is of the order of 1 by 2 alpha or 1 by alpha. And from Schrodinger equation also we have obtained the same result. From here, this part, we can say that delta x penetration depth is of the order of 1 by alpha. So we have seen that this quantum tunneling, that the particles are penetrating up to some distance, even though the energy, total energy is less than the height of the potential barrier, this result is consistent. It's consistent with the uncertainty relationship between energy and time. And one example, again from the case of photons, is that if light is incident on a metal surface, suppose you have a smoothly polished, completely polished metal surface, a mirror-like metal surface, then the light is incident on the metal surface and it is reflected back. All the light is reflected back from the metal surface, polished metal surface. So reflection probability is 1. But still, this is an electromagnetic wave. So when it is incident on the metal surface, some electromagnetic field, some varying electromagnetic field is generated within the metal, inside the metal surface, within the bulk of the metal. But we cannot say that the light is penetrating the metal surface and traveling inside. It is transmitted. No, light is not transmitted. All the light is reflected back. But still, the electromagnetic field, varying electromagnetic field of the incident light penetrates to some distance within the metal surface. So it's an exponentially decreasing situation. The electric field will be electric field and magnetic field will be exponentially decreasing up to some distance, and then all the light will be reflected back. And this distance, this penetration depth in the case of metals, electromagnetic field in the case of metals is often called skin depth. Okay, so this is a measure of the skin depth. We can say 1 by alpha. This penetration depth. So in the case of light, this type of phenomenon can happen, and frustrated total internal reflection is another incident, another situation where this type of quantum tunneling to another region can happen.